Welcome to this video on a quick anatomy lesson of the wave and types of electromagnetic waves. Some of the foundational language that we're going to use to understand waves is really important before we jump into all the cool things waves can do. So let's jump into it right away. A wave can be described by several different properties, and one of them is the wavelength or the period of the wave. And that's actually how long it takes one full wave to occur. So let's think about this. We said that a electromagnetic wave was created by an oscillation of, in this case here, an electron. So the electron oscillates up, back through its equilibrium position that it's at right now, oscillates down and returns to equilibrium. So one complete up, down, and back motion is one complete wave cycle. So I'm going to go ahead and graph that one complete cycle here. So I'll say that it reaches its peak over here, it's going to go back through equilibrium over here, and it will reach its crest or its trough over here and repeat the cycle again. So if I map out what happens there is the wave displaces up, passes back through equilibrium, displaces down, passes through equilibrium, and back again. And this motion continues over and over again. And we know that that's going to create an oscillating electric and magnetic field. Now, looking at this basic wave shape over here, what we're going to do is describe the displacement or the maximum displacement from the horizontal axis as A, and A is going to represent the amplitude of the wave. Now, the amplitude of the wave in this case is a position amplitude, but you can also have velocity amplitude or acceleration amplitude if you're looking at a different labeled axis over here. Here we're just looking at displacement and time. Now, other things are that the high points of the graph, or these maximum values, are crests, and the low points are troughs, or you can sometimes refer to them as peaks and valleys. Some more important terms, however, are the time that it takes to make one complete oscillation. So it's going from equilibrium here, back through equilibrium, and returning. So that one full motion that has occurred, I'm going to say occurs from here to here. Now that can be described in two different ways. We can describe the time that that takes to occur, and the time that it takes to make one complete wave is known as the period of the wave. And that's of course going to be measured in seconds or some other time measurement. The length of that in terms of the wave is going to be referred to as the wavelength. So we're not measuring the entire wave stretched from one place in space to another, but just specifically the length of one complete oscillation or one complete wave. The wavelength is measured in meters. Okay, so a period and a wavelength are kind of the same division on the graph, but the period is describing the length of time that that division happens in, and the wavelength is describing the actual length of that grouping of the graph. Now we use the Greek letter lambda to describe the wavelength, and then we use uppercase T to represent the period. Now, one other thing that's very interesting is that in order to actually measure the period of oscillation, it's usually very difficult if this thing is moving very fast. You know, your reaction time to time this would be really difficult. So what we'll oftentimes do is say, let's count how many oscillations it can make in, let's say, 20 seconds or 10 seconds. So let's say that 20 oscillations occur, and those 20 oscillations take a total of 10 seconds to occur. Now if I simplify this fraction down, obviously I get 2, and that would be 2 oscillations per second, or 2 cycles per second, or 2 complete wavelengths per second. And what we're actually describing in that case is known as the frequency of the wave. Now frequency units are going to be either second to the negative first, or that's known as, more commonly, a hertz. we symbolize Hertz with Hz, named after Heinrich Hertz, who we will talk about in a little bit, who was one of the actual first discoverers of the experimental evidence of electromagnetic waves. Now, the term frequency is important in getting to period, like I said, and the reason that that happens is because the frequency is oftentimes easier to measure. So if I said to you the frequency of the wave was 20, how frequently it occurred 20 times every 10 seconds, well then how long did it take to make just one complete cycle? Well, rationally, that's actually very easy to figure out. So I measured the frequency, and now I want to calculate the period from that. So rationally speaking, if you can do 20 of those in 10 seconds, then each one is going to take half a second to complete. So the period is actually going to be the inverse of the frequency. So we could write it in this way. The period is equal to the inverse of the frequency, because if the frequency is the time it takes to make X number of different cycles, and the period is the time it takes to make one complete cycle, then I should do 1 divided by that time. So in this case here, half a second is the time it takes to make each cycle. Now, it turns out that the frequency is an extremely important descriptor of waves in general. And specifically for electromagnetic waves, the frequency is going to be very, very important in identifying what classification or category of electromagnetic wave I am describing or measuring. What's extremely important here is to think of an example. So let's start with an example here. Let's say I have a sheet of glass. Now I'm looking at it from the side, and let's say I shine a red beam of light, or actually let's make it green. We have a green beam of light. The light passes through the glass and we see green light on the other side. So the color of the light did not change as I saw this occur. It's kind of like thinking about if I shone a green light at the glass, but then purple light came out on the other side. That doesn't actually happen, and that tells us something very important. Now, you might be thinking, well, if you shine white light at a prism, it does change into lots of different colors, and that's a little bit different. We're going to take a look at that a little bit later. The idea here that I'm trying to get across is that frequency is considered to be source dependent. That's extremely important. The frequency of an electromagnetic wave is source dependent. Source dependent means the original little, let's say in this case, electron that was oscillating is the source of the electromagnetic wave. And the frequency with which it oscillated defined what that wave frequency was going to be forever onward. So frequency is dependent upon the source and not dependent upon the medium that it encounters. Now this is important because it's not as logical for some people as others, but what we're going to do is take a look here that if frequency is always a fixed value for a specific wave that we're studying, then other things about the wave are going to have to change if it enters a new medium. Let's see why. Let's describe the speed of this green light. Let's say that the speed of the green light is going to be represented with the v for velocity or speed. So we'll define here that we're looking at the speed. Now, I usually could calculate the average speed of something as its displacement over time, or it's the distance it travels over time. Here, what we're going to be able to do with waves is, in order to describe how fast a wave is traveling, I can actually just take its wavelength and divide that by its period, and that will tell me how long that increment of the wave took to occur. And if the wave is traveling at a specific speed, that would be the same speed as the wave. Now, because we have this relationship between period and frequency, I can actually say that the speed of the wave could be equal to the wavelength of the period, or the frequency times the wavelength, and both of those things are the same. Now what I just said was that the frequency of the wave does not change when it enters a new medium. So if the frequency of the wave as the light enters from air into glass, if that changes position and the frequency does not change, then that means that the speed and the wavelength have to change if frequency is constant. If we think about this, if we were to make a little graph here to conceptualize this idea, let's put the speed on this axis and the wavelength on this axis. And if the frequency is constant, what we're basically saying then is that, let's say I graph this line here and this slope of the line is frequency. It means that if that can't change, that rate can't change, then the wavelength speed ratio has to stay the same. But that doesn't mean that the speed on its own has to stay the same or the wavelength on its own has to stay the same. It's just the ratio of the two have to stay the same. And that's actually what we find happening. So unless the source changes, the frequency will not change, but the speed and the wavelength will change. Now it turns out as light goes from a less dense medium, such as air, into a more dense medium, such as glass, the wave speed will actually decrease, meaning that the wavelength will have to also decrease in order for the frequency, as we observe, to remain unchanged. Now, because frequency is source dependent, we actually describe different classes of electromagnetic waves by what their frequency is. Now, in a vacuum, electromagnetic waves have been found all to travel at this exact same speed. Now, that makes sense because if multiple different electromagnetic waves are generated and they're all traveling in the same medium, they should all be maintaining the same speed. And that speed we give a special letter to, c, which is known as the speed of light. And I'm putting light here in quotation marks because light is actually what we interchangeably use for the term electromagnetic waves. So it's the speed of electromagnetic waves, or what we sometimes generically refer to as light waves. This speed is around 300 million meters per second, or about 3 times 10 to the 8th meters per second, really more like 2.9999 something times 10 to the 8 meters per second. But what we see is that if the speed is something very constant, then different wavelengths will have different frequencies, or we could say different frequencies will have different wavelengths. So if the production of the wave is a very long wavelength, so I'm going to go ahead and put here a long wavelength on this end of the spectrum, and over here a much shorter wavelength, or a short wavelength, I'm going to also write that in terms of frequency. A long wavelength would be a very low frequency, because they have an inverse proportion if the speed is constant, and a very short wavelength would therefore be a very high frequency. But remember, this is only true if the speed is constant, because sometimes people assume, oh, okay, well, if this particle travels, or if this light, travels from a less dense to a more dense medium, well, if its frequency stays the same, its wavelength must stay the same, because those two things are inversely proportional. So if I don't change one, the other one won't change. That's not true, because the speed is changing in that case. Here, because the speed is constant, we can say that these two things are inversely proportional. Now it turns out if the source of the electromagnetic wave creates a wave at a very low frequency, we refer to that category as a radio wave. But remember, these terms are just terms that we gave to these different classifications or different parts of the electromagnetic spectrum because they were not all discovered at the same time. So we have to be careful that a radio wave is not something different than the next wave up here, which is actually going to be a microwave. It's just that they're produced with different frequencies. So we have radio waves, we have microwaves, we have infrared waves. We then have what we refer to as visible electromagnetic waves, or sometimes known as visible light. And if you think about infrared, we know that the different colors that fit into this segment are that we have the rainbow colors here. We have red, and infrared would mean below red. And the next category up will actually be ultraviolet. And so the other end of the visible spectrum is actually violet, because this is going to be ultraviolet or above violet. And we'll put all the other colors here in between. So we have ultraviolet, then we're actually going to have X-rays, and then what are known as gamma rays. And sometimes we put cosmic rays and other things around here, but these are the main and most accepted forms. Now, these are not all different kinds of waves. They're just waves that, depending on the source production of the wave, the frequency fell into a certain range, and so we refer to them as radio or micro or visible light, and so on and so forth. Each of these different little categories has a pretty distinct boundary on either side. So visible light occurs between very specific wavelength values or very specific frequency values based on what the human eye can actually detect. So your eye is actually evolutionarily adapted to be able to detect waves that have a frequency between these two different values. However, our eyes are not able to detect in the same way ultraviolet or X-rays or radio waves or microwaves. So we can't see radio waves in the same way that we can see visible light waves because of the frequency of the wave. So this video is a little bit longer, but important because we have to make sure that we understand that frequency is source dependent, but speed and wavelength are what we refer to as medium dependent. So we'll take a look in the next video at how waves behave when they hit a boundary going from less to more dense or more dense to less dense.